Good morning, guys. So I had to take the whole day off, so I apologize for that. But I'm gonna go through the notes real quick. Try to make this a short video, so feel free to pause, fast forward as you need to, or rewind, obviously. And then any questions that you have, I can obviously answer tomorrow when I get back. I apologize as well if you hear my girls screaming or yelling. They'll be getting up here in a moment and being crazy, I'm sure. So, all right. Warm up math talk. First thing, rewrite the following as a power of 2. So this is something you guys should have learned last year, but we're still going to do this anyways. So this is a base times a base. This is really like saying 2 times 2 times 2 times 2 times 2 times 2 times 2. Right? So when you have 2 to the third times 2 to the fourth, you actually have 2 to the seventh. Okay, so what you're going to do is when you have a base times a base, you're going to add the exponents. Okay, same thing here. So this is 2 to the fifth times 2. Well, this is an imaginary 1 up top, right? It's not a 0. It's an imaginary 1. So this is really just 2 to the sixth because you would add the exponents. Okay, so when we multiply, if we're adding the exponents, then when we divide, as we mentioned yesterday, you're gonna subtract the exponents. So this is really like 2 to the 10th over 2 to the 7th. And as we talked about before, it's like saying 2 times 2 times 2 times 2 times 2 times 2 10 times. Let's see, that's 6, 7, 8, 9, 10 over 7, 5, 6, 7. And what you realize is that these all cancel out, leaving just 3 up top. Okay, so that would be 2 to the third over 1, or just 2 to the third. So again, subtract the exponents. Same thing here. So you have 2 to the ninth divided by 2 to the first. There's an imaginary 1 up there, even when we don't say it, even though it looks like it's just a constant. Okay, so that's actually going to be 2 to the 8th. Okay. So moving on. So today we're talking about exponential growth. So we're going to go through a few more of these exponential things and then kind of go from there. But it says complete the table, take advantage of any patterns you notice. So the first thing that we notice is that we have an X column and we have a Y column. This says Y is going to be 3 to the power of X. Sorry, 1 second. Thought I just heard the baby crying. Which means I'm pretty sure that was the baby. So this is going to be, it says 3 to the fourth, basically, if you plug that in, right? This is going to be 3 to the fourth. This is going to be 3 to the third, which means this is 3 squared, which means this is 3 to the first, which means this is 3 to the 0. Now, what we realize, though, if you know your math facts a little bit here, is that we go from 81 to 27. What we're doing is dividing by 3. Okay, now we know that 3 squared is also 9, and 3 to the first is 3. And so you can kind of see that pattern as I just talked about. Divide by 3 to get to here, divide by 3, get to here, divide by 3, get to here, and then divide by 3 again gives you 1. So as we talked about yesterday, anything to the 0 power, any number, so let's say a to the 0 is always going to be 1. Okay, any number to the 0 power. Okay, here's some new equations. Find the solution to each equation using what we know about exponent rules. Be prepared to explain your reasoning. It says 9 to the blank times 9 to the 7th equals 9 to the 7th. Well, if it's still 9 to the 7th and this is 9 to the 7th, we talked about a base times a base. What number would I need to add to 7 to get to 7? It'd just be 0, right? So in this case, the x would be 0. Or the question mark, I guess. Okay. Same thing for part B. Part B, we've got 9 to the 12th over 9 to something. It maintains 9 to the 12th. So that's going to have to be 9 to the 0, right? And then lastly, it says, what is the value of 5 to the 0? What about 2 to the 0? So again, just summarizing here, anything to the 0 power we know is going to be 1. Okay. So, exponential growth. This is kind of what it is here. It says, in a biology lab, 500 bacteria reproduce by splitting. Every hour on the hour, each bacterium splits into 2 bacteria. So, splitting every hour, okay? So, when it splits, obviously it doubles. It says, write an expression and show how to find the number of bacteria each hour after each hour listed in the table. All right. Well, the first thing we know is that we're going to multiply by 2, right? So, whatever number we start with, let's call that A. We multiply that number times 2. Okay, so in this table, since it's splitting, we start with 500, then it becomes 1,000, then 2,000, then 4,000. But now pay attention, it goes all the way up to 6 and all the way up to t, so we have to be able to figure that out, right? So it says, write an equation relating n, the number of hours, to t, the number of hours, or number of bacteria, to t, the number of hours. Well, so what's happening is we have this starting value, 500, and it's being multiplied by 2, but it's happening every hour. We need to figure that out. Well, this equation is going to end up being like this, where it's an exponent. Okay, and we do that because we've already used the multiplication. So we started with 500, we multiply by 2, and we raise that to the power of t because that's the number of hours. Okay, so here's your equation to find n when t equals 0. So we'll say that this actually could be n equals 500 times 2 to the power of t. Okay, well, let's first do it with 6 because that's going to help us out, right? So n equals 500 times 2 to the 6th power. So 500 times 2 to the t, by the way. Okay, because we don't know what t is. 2 to the 6th power is, let's see, that would be 2 times 2 is 4, times 2 is 8, that's 3. Let's see. Write it out here. So we've got 4. 2 times 2 is 4. 2 times 2 is 4. So I've got 4 times 4, which is 16. 16 times 4 would be 64. So to the 6th power would be 500 times 64. Now, you guys have the benefit of putting this in your calculator. I, of course, do, but I can just do the mental math here. Well, the math from what I've learned in way back when. So when you have 2 zeros like this, I'm going to write it off to the side, bring them down. Little trick of the trade, right? 5 times 4 is 20. Carry the 2. 6 times 5 is 30. Add the 2 gives you 32,000. So to the 6th power is going to be 32,000. Okay. Then number 2 says, in a different biology lab, a population of single-cell parasites also reproduces hourly. An equation which gives the number of parasites p after t hours is p equals 100 times 3 to the t. Explain what the numbers 100 and 3 mean in this situation. Okay, so if you looked above in our formula before, we had 502. In this one, we have 103, but it still looks pretty close to the same thing, right? So what do we think 103 mean? Yep, that's right. 100, starting value. So it's like our y-intercept. Okay. 3 means we are tripling the value. Okay, or multiplying by 3. Sorry for the handwriting. Okay. So we've got multiplying by 3 and starting at 100. Which brings us to our next point, which is kind of what we wrote up here. There's an exponential growth model, aka a formula for exponential growth. Again, equations that look like this. Okay, that have this huge curve and they start really slow, like we talked about with the purse yesterday. That model looks like this. Let's see, we could call it f of x equals a times b to the power of x You could say y equals a times b to the x. Or you could even say, let's say we put t in there. So we could say f of t equals a times b to the t, where t is time. So sometimes you'll see it as x if it's just, x value on the x-axis, or sometimes you might see it as t. So primarily we're going to use this version of it, but sometimes we'll use the other ones. Okay, refer back to your work on the table of the previous task. Use that information given coordinates to graph the following. So graph t of n when 0, 1, 2, 3, and 4. Well, this, if you recall, when we used t and n, this was the n equals 500 times 2 to the t. So we're going to graph this one, which meant that it started at 500. Let's see, this is 1,000, so 500 would be about there. And it doubled every time, every hour. So that would be at 1,000. And it doubled from there and got to 2,000. Doubled from there and got to 4,000. Doubled from there and got to 8,000. I just got to mark it to see. Let's see. Here's 4. 8,000 would be there. Okay. So that's what the graph would look like for 500 bacteria that are splitting by doubling. Okay. And then the other one, which was 100 times 3 to the p, well, same idea, but now it's starting at 100. So let's see, 500 would be here. So this would be 250. So 100 is probably about there. And it triples, so that would be 300, which would be about here. Then 600, which would be about here, because that would be 750. Then 1,800, which is, let's see, this would be 1,500, 1,750. This would be a little bit above that. And then triple the 1,800 would be 5,400. So that would be, let's see, about here, because this would be 5,500. Okay, so that would be the graph. Oops, it's not very good. That would be the graph. And you can see they're pretty close to the same. The only difference is that look how the second one is actually increasing a lot faster. It started lower, but it increases faster. By the time I get to 4, I'm already over 8,000, right? In fact, by the time I got to, 4 would already be 8,000. 4 here would be 5,500. Okay. So finishing up. On the graph of n, where can you see each number that appears in the equation? Where can you see each number that appears in the equation? Well, you can see it at the values of t, right? But specifically, the 500 is the y-intercept. And 2 is the fact that the y values are doubling. Okay, on the graph of p, where can you see that each number appears in the equation? Same idea, 100 is the y-intercept. But now 3 means the numbers of y values are tripling. Now, a good way to practice this, of course, is to plug all this into Desmos and try it out that way. So let's see. Where's Desmos? Okay. So in Desmos, you can type this in. Y equals 500 times 2 to the... You're going to use this button right here, the A to the B button. And then raise that to the power of x. Okay, so there's that one. What you can see is I need to zoom out. There we go. Starts at 500. See, it looks kind of like that. And then you have the other one, which is y equals 100 times 3 to the power of x. And there's the other one. So you can see the red one actually starts a little bit higher and it goes out a little bit further. But because the blue one has a higher, like it's tripling and not doubling, the blue is actually going to end up going up faster than the red one. Not initially, of course, because it's got a lower starting value. But over time, it will definitely overlap it. So anyways, that's exponential growth. I know it's a little bit confusing, me not being here. I'm going to make a practice key for both today and yesterday. Take a peek at that. Let me know if you have any questions, and I'll see you guys tomorrow.